Okay, everyone, so what I'm going to talk about today is acetal formation and acetal hydrolysis. So I'm going to start with acetal formation. So, remember when we talked about hemiacetals, hemiacetals are always in this equilibrium between the ketone or aldehyde and the alcohol, and they're in equilibrium with the hemiacetal. So they're in equilibrium, and this equilibrium really lies very far to the left. There isn't much hemiacetal in formation. But what actually can happen is you have to realize that there's lots of this alcohol floating around. There's a whole lot of it floating around. So the ketone doesn't just have to react with one molecule of it. If there is any acid at all, H+, then what can happen is with a little bit of acid catalyst, you actually get the hemiacetal it's there in equilibrium, so there's a small amount of it, but the hemiacetal will actually react with another molecule of the alcohol and form an acetal. And so because this reacts the hemiacetal and removes it out of the equilibrium, and this equilibrium lies a little bit far to the right, it starts pulling the whole system all the way to forming acetals. So this means that with the addition of acid, you don't get hemiacetals, but acetals begin to form. So we get an acetal. An acetal is an organic compound with two alkoxy groups on the same carbon. So just like with hemiacetals, it doesn't work if the two groups are on different carbons. They've got to be on the same one. So here's the functional group for an acetal, whereas a hemiacetal has an H in place of one of the R groups. So hemiacetal is this. So this is one of our many relationships where there's a R group swapped for a hydrogen. So this is a very common relationship in organic chemistry. So this is this is the acetal. So how it forms, I pretty much just mentioned. I just went over that briefly, but here we go. The acetal is, and I'll just do these problems to show you how it works. The acetal is formed by, what happens is the alcohol attaches itself in place of the hydroxyl group. So now, before, with a hemiacetal formation, it's all self-contained. There's no sloughing off of any atoms. There's no water or hydrogen or anything given off. But with acetal formation, there's an oxygen here and a hydrogen here and an oxygen here and a hydrogen here, and we end up with only the oxygen being used in the alkoxy connection. So here is what I had before. Here was the part of the hemiacetal that was there before, and now the alcohol gets attached here. So this is the oxygen that was there, and it's not clear which, and it doesn't even matter which of these two oxygens is the one that stays, but one of the two oxygens stays, the other takes one hydrogen with it and goes, it takes two hydrogens with it and goes away. So there's my other oxygen forming water. Here we have I'm asking you to go backwards. So we have the acetal, and I want you to draw the hemiacetal that it came from. So this must have been which of these two alkoxy groups? This alkoxy group here must have come from this ethanol, whereas this alkoxy group must have been part of the hemiacetal to begin with. So our hemiacetal that we started with is this. CH3. So that must have been there to begin with. The H was there to begin with. What was in place of where we have the ethanol group here? The ethoxy group. It was a hydroxyl group. So what happened was this ethanol replaced the hydroxyl, made an alkoxy group and an ethoxy group, and the water was kicked out. Here, let me do a few more. There we go. So here we have, so if I've got something like this, so here is my acetal, or sorry, hemiacetal, and I'm going to react it with this alcohol. I'm going to react it with, let's react it with ethanol. What would we get? What's our final answer here? So take a moment, pause it, and draw the structure of the acetal you'd expect to get. So of course we have to, this reaction ends up being with a little bit of acid catalyst is the reaction we get. And now, so we have an acetal. So this part stays intact. Now I'm writing a slightly different conformation just because of the space that I have available to me. So here. Now this part, this isopropoxy group here stays the same, although I gave the wrong number of hydrogens up here a moment ago. Should be just one hydrogen, and still just one hydrogen down here actually. So let me fix that. And so now we attach over here where the hydroxyl group was, we're going to attach that ethyl group. Right? So now we have an ethoxy group where the hydroxyl was. So that is an acetal formation reaction. Now related to that is a reaction that where acetal is the reactant. So acetals are easily isolated. Sorry for that little hiccup. They're stable in basic solution. But in acidic solution, they undergo hydrolysis. They fall completely apart. So a hydrolysis reaction is another broad type of reaction. We've been talking about all these different names for reaction types. A hydrolysis comes from the word parts hydro, which means water, and lysis, which means lyse means to cut. So we're cutting with water. We're breaking a compound apart with water. So we get, in this particular case, with an acetal hydrolysis, there we go. In an acetal hydrolysis, we always get the same products. They're the parts that the acetal is made up of fundamentally. So we always get two alcohols that may be the same or different, and we get an aldehyde or a ketone. So to draw all over this again, you see that my two alcohols are here. They're the alkoxy groups. The alkoxy groups are the alcohols. And then what's remaining, this part, is the aldehyde or ketone. So let's look at some practice here. So I'm going to use down here at the bottom as the place to draw all the answers for this. But so for this first one, what we have is we have two methoxy groups and this ethane chain. So the question asks us to draw the structural formulas for products that result after acetal. These acetals undergo hydrolysis. So this first one is going to give me two methanols, because these two methanols here are those two methoxy groups become methanol. So what's going to happen is we're going to add H2O, right? So we're going to add H2O. We'll get two methanols. And we'll get the rest of the compound, which is the CH3, and the CH goes back to being either an aldehyde or a ketone. So you see, here we only have two oxygens total, but down here we have oxygen, oxygen, and this is times 2, so there's 3 oxygens. So this addition of water is necessary because one of the oxygens hangs onto the now forming aldehyde. One of the oxygens goes with one of the methoxy groups, and one has to come from the water to go with the new alcohol group. So that's what we get there. This next one over here, we have two methoxy groups, which are going to give us two methanols. And then what we're going to get here is the rest of the compound is CH3, CH, CH3. And I guess what we get is we get a... And up here, this was a mistake. So this should be a two hydrogens. So we do lose a hydrogen off of here. So I've got to erase this hydrogen. So this is what we get. We get propanone. So we get two methanols and a propanone, again, coming from the parts of the acetal. Here, this one, here is one, there's a methoxy group and an ethoxy group, and the rest is a 5-carbon chain. So we're going to get methanol, ethanol, and this compound, we'll get 3-pentanone. So that's our compounds from that one. And finally, this last one here they are. Again, we'll get 2 methanols. So we're going to get two methanols. And the remaining is right here. So this is actually going to give us this compound, which is, looks like 5 carbons. So that's going to be pentanal. So I hope that makes sense. The acetal formation hydrolysis isn't that bad. So hopefully this helps.